Bismillahirrahmanirrahim. Assalamu alaikum. This is our 37th lecture of Formal Methods for Software Engineering, and I am Fakhar Lodi with you discussing Z specifications. In the previous lecture, we saw an example of an insulin pump and the Z specifications for that insulin pump. And one of the things that we touched upon was the issue of consistency in specifications. Today we shall discuss the path from specification to implementation. How do we convert these specifications and add more detail into these specifications so that we can ultimately achieve something which is closer to implementation, which can be executed, which can be compiled and executed, and we have our program there. The road from specification to implementation is what is called schema refinement. What happens is, as I mentioned in the last lecture also, our specifications, they are relatively speaking at a higher level of abstraction. What we usually say is what is to be done, what is the requirement, what are the characteristics, what are the properties, what are the predicates, what are the invariants. We do not talk about how. Specification is about what and not about how. So when we say what, this whole thing is, relatively speaking, at a higher level of abstraction. For example, if I say that, I need to build a house, and these are my requirements, that is, and these are my constraints, that is, let's say I have a plot of 1 canal size, and then my requirement is that I need to have 2 floors, and then I need to have 4 bedrooms, a kitchen, drying, dining, and so on and so forth, lounge, whatever. So I give these requirements to my architect. So I tell the architect about my overall constraints in terms of the cost, in terms of the area, and so on and so forth. And I also tell the architect what do I need, how many bedrooms, what are the other things, and so on and so forth. Now, this is what the specification is. This is what I need. It still is at a very high abstract level. There is nothing concrete there. So the architect has many different choices to realize, to implement, to give me what I need. So as the architect will move on crystallizing the idea, transforming this requirement into a plan of implementation, a layout, more detail will be added. And as, for example, once I say that, I need these 4 rooms, and the architect sort of has this plan where, I have 2 bedrooms in the ground floor and 2 bedrooms in the first floor. Now, this is one way to achieve that requirement. But once that plan has been, put there, that means now I have more information how this whole thing will be realized. My requirements have been refined from just a very high level idea of what I need to somewhat more detailed kind of plan. Now I need 4 rooms, 2 rooms will be here and 2 rooms will be there. So what my point here is that, when we move from requirement to implementation, we keep the requirement in mind. We do not violate the requirement. I need 4 rooms, I get 4 rooms. But where these rooms will be, that is part of the detailed plan. And once I have added that detail, I have sort of map on a piece of paper that tells me where my different rooms will be and where are the different pieces and so on and so forth. I have added more detail to my abstract requirement. I have not violated those requirements, but now once I have put those requirements, my choices are, relatively speaking, limited now. Before, I had given this thing that 2 rooms will be here and 2 rooms will be there. I had lots of choices. Now once that part is fixed, although it is according to the requirement, but the number of choices that I have is fixed. So I have added detail. This addition of detail has reduced the choices that I have, but at the same time it has taken me one step closer to actual realization of the requirement, actually having that house. The same is the case with our specifications. So what we do is we start with high level abstract specifications where we simply tell what, and then slowly we keep on adding detail, and this detail, we cannot violate the requirements that we have specified previously, but we refine those requirements. As we refine those requirements, there are a number of things that we need to know, we need to take care of. The first is consistency. As I add more detail into my requirement, I need to be consistent with my previous requirement. So my new requirement is sort of built onto the previous requirement without violating what I have said before. It cannot. So it has to be consistent. So when I will be adding detail, when I will be refining that thing, I need to be consistent, and somehow I need to make sure that I'm consistent. The second is, of course, correctness. All these requirements, they have to be correct. So every step that you take, although it builds onto the previous step, it refines the previous step, but it cannot violate and it cannot be incorrect. So these are basically what we are going to discuss in the lectures today and after that. Let me go back to the slide and show you with some examples of what this refinement means in terms of software and the mathematics behind this refinement, and then the Z schemas when we refine schemas, older schemas, and get the new schemas. So let us go back to the slide and have a look at a very simple example and scenario. Here is the example of an abstract data type, which is a combination of a description of state with the description of operations upon that state. So we say this abstract data type A is equal to a state, A init, and A op1, A op2, other operations, and so on and so forth. So the abstract data type A consists of three basic things. How do we define the state? The abstract data type has to have a state, has to have a mechanism for initialization, and supports different operations. So this is a very abstract definition. Now we have this very abstract definition of an abstract data type A. When we actually realize this abstract data type, we have a number of choices. For example, we say, okay, we are going to implement this abstract data type in C++, and we are going to use a class to represent this abstract data type. So when we will have this class, in that class we say class A, then there will be certain variables. Those variables will specify the state. So I have the state for my abstract data type. That state takes a concrete form in the shape of the variables in my C++ class. For initialization, I have a set of constructors in my C++ class. And each operation that I have given in the specification of my abstract data type, I will have each operation converted into a method that is supported by that C++ class. So I have an abstract definition, abstract specification of an abstract data type. I have a concrete implementation of that abstract data type in C++. This implementation may not yet be complete, but it is, if I just give a header file, this specification is closer to my actual implementation, the header file. At least I have converted this abstract data type into C++ syntax. So this is one example of converting something into more concrete thing by actually adding detail. So when we move from what to how, we are actually adding detail. With every step we add detail, and we take one step closer to the actual implementation, that is, how are we going to do it without violating our initial contract or initial specification. Let us go back to the slide and look at some of the refinement steps. Refinement means removal of some degree of non-determinism, and several refinement steps may be performed until the specification approaches executable program code. This is basically saying the same thing again. We start with an abstract picture. So what we do is we refine it. When we refine it, we add detail. When we add detail, that means we limit our choices. When we limit our choices, that means some degree of non-determinism is removed. जब आपके पास एक बिल्कुल abstract चीज है, so there is this non-determinism, you can implement this thing in so many different ways. So that is the non-determinism. So each step that we take towards actual implementation removes that some degree of non-determinism and is moving closer to a concrete form of the actual requirement. And we may take several refinement steps. आपने abstract data type बिल्कुल abstract mathematical फॉर्म में उसको डिफाइन किया. You start with C++ header file. So this is one refinement step. That header file you will be at, this still is kind of a lot of what. But when we look at the operations, there is this particular operation that we need to perform. There is this particular data structure that needs to be maintained. How are we going to perform that operation? The algorithmic steps and all that still is specified at an abstract level. I only talk about what the operation is. I'm not talking about what are the algorithms that I'm going to write in order to perform that operation. So this is still to a large extent what, but we have added some information that will lead us, take us closer to how. Now let us go back to the slide once again. We have these questions. Why might we want different views of the same system? What makes two different views consistent? And what makes two consistent views different? We are refining the specifications. That means each refinement step is kind of presenting the same specification from a different angle with some more detail added to it. So the angle changes. If you add detail, for example, you implement it in C++, you would have one form. You implement it in Smalltalk, you will have maybe slightly different form. But it is a view, it is a different view of the same specification, of the same problem. The questions which seem to be trivial, but they are not very trivial, are, like I mentioned, first of all, why do we want to have different views of the same thing? One answer to that is, what I want to do is, I want to take this abstract specification and move towards my concrete implementation. So when I add detail, this is a different view of a previous specification. Now, the second question, which is a very important question, is, now we have two different views of the same problem with different levels of details. How do we say that these are consistent? So, your consistency, how are we going to define consistency? How are we going to say this is consistent with this? And the third, which again seems to be a trivial question, but it is not a trivial question, is if we have two consistent views, what will make them different? How will we say that these are different? What are the things that we have to look at to say that these are different? So our discussion from now on is going to focus on these questions: the consistency and the differences among different views. So we will look at the mathematical foundations of consistency, and we'll see from a mathematical point of view what is different and what is consistent, and then what kind of refinement steps are permissible and what kind of refinement steps will make it inconsistent with the previous specifications. So let us go back onto the slide and look at this mathematical formulation. Refinement relation. We say data type B is a refinement of A, and it is written as A is This is slightly different from the subset, okay, but it looks very, very similar. In a subset, we have a curve here, but in this, the notation that we are using, this is more kind of a squarish notation, but it looks very, very similar to a subset. So we will use this refinement, we will call it a refinement or a proper refinement. So B is a refinement of A if and only if every interaction with B could have been an interaction with A. Now this is very important concept here. I have an abstract version of my problem. And when I refine, this refinement is one possible form of that abstract version. My abstract data type, I refined it with C++ class. That is one possible form of that original abstract data type. What I'm saying here is, B is a refinement of A if every permissible operation on B is also permissible on A. We are not violating the original contract. If we violate, that means it is not going to be a refinement. So this is an important concept. Please keep this thing in mind. Let us go back. If this is the case, that is, if and only if every interaction with B could have been an interaction with A, if this is the case, then B will be a worthy replacement of A, whatever the context. That means that, when we say that B is a refinement of A, that means we can replace A by B and it will fulfill the purpose. It will not be that generic because we have taken some of the flexibility out. We have removed some of the non-determinism, but it still fulfills the purpose, and hence A can be replaced by B. Then we have the definition for a proper refinement. We say, it is a proper refinement if it is quite possible that A is a refinement of B, but B is not a refinement of A. This will be the case when description B has resolved some of the uncertainty present in A. The effect of A, at least one of the operations, is now more precisely defined. Now, proper refinement is a refinement in which some uncertainty has been removed. If A is a refinement of B and B is a refinement of A, that is, A can be replaced by B and B can be replaced by A, then these are equivalent. It is improper. So it is only one way, that is, B is a refinement of A. That means we had some flexibility, some non-determinism in A. We took some of that out. We still kept that contract, but we now has more concrete form. And it has more precise structure or formulation. So hence it can replace A. So this is the proper refinement. Refinement ordering. If B is a refinement of A and C is a refinement of B, then C is also a refinement of A. Now this obviously is a very, very trivial and simple concept, but it has far-reaching consequences. It basically says that, we start with A, we refine it, we get B, we refine it, we get C, we refine it, we get D. Now this D is a refinement of A because the original contract cannot be violated. in every step we are reducing the non-determinism, we are reducing the flexibility, we are reducing the number of options that are available to us, but we still maintain the original contract. So this is kind of a refinement step, and with each step we are getting closer to the implementation. So this is the consequence of this, that you can take many refinement steps and you will still be in line with the original specification, and A could be replaced by C now. We don't have to replace A by B and B by C. A could directly be replaced by C. Here is an example. We have this resource manager A, in which we have the state variable free, and we have an operation allocate A, which changes this resource manager A, and there is this output variable R, which is of type N, and we say R is a member of free, and the new value of free is equal to free minus R. So we have this set of values from which we take this value R. This value is among the values that are present in C. So after we have allocated this resource, we have taken it out from the set of free resources. Now the question here is, if there is more than one available resource, then this specification is non-deterministic. How is it non-deterministic? What we are saying here is that we have a free set of resources, and we have given maybe them certain numbers, and we say allocate, and this takes one free resource from this free set, and that resource is you give that an output, and it can be used anywhere where that output is used. And now we have taken this free resource that has been allocated from the free set. So the new value of the free set is the old free set minus this new element, this element that has been allocated. Now the question is, where is the non-determinism? Non-determinism is that if I have 10 resources, which one of these 10 would be allocated? This allocate method could allocate any one of these. Now it could be a random function, it could be a minimum, it could be a maximum, it could be least recently used, whatever. I am not specifying this thing here. I am only saying I need a resource. If there is a resource present in the free set, give me that resource and update the free set. So this is the allocate. And which resource? I'm not talking about that. So from that point of view, this is a non-deterministic, and we will be adding detail, making it more deterministic. At the same time, this definition is partial. Partial means that this definition is not complete. It does not tell us what will happen if we cannot allocate a resource. There is nothing in the free list. There is nothing in the free set. The free set is empty. What will happen? So when we enhance the schema, when we refine the schema, we add those details, not just the detail for the error condition, because when we add detail for the error condition, this once again is a refinement step, and we have to keep ourselves aligned to the original specification. At the same time, we will try to reduce the non-determinism from this specification. So let us go back and look at the refined schema for this problem. Now we have this resource manager B. Now I have this free B. So this is a new schema. And allocate B updates resource manager B. And I have the same output variable R. Now my predicate says R is equal to minimum of free B, and free B is equal to free B minus this element that has been assigned. Now in this particular case, what we have done is we have specified which particular resource will be allocated, and we have said that the resource with the minimum number associated with that, whatever that means, minimum in the free set, that is the resource that we will take and allocate when this request is made. So there is this step of refinement. We have refined it. We have taken the non-determinism out, but it is still partial because the error condition is not specified. So this new specification B is a refinement of A. Non-determinism has been taken out. Previously we had this thing that we could allocate any resource from the available free set, but here we say this particular resource, the resource with the minimum number, would be allocated, but we still need to refine it to make it complete, to handle the error condition. So this is one example. Now let us go back and look at a refinement step which takes it to the next level. Now we refine it to the code. The refinement of state components and operations can take us to executable code. We replace the components of the state, that is sets, relations, sequences, with data structures from our chosen implementation language. So we resolve any non-determinism present in the description of the operation. So this is our new resource manager D, in which this free D is an array of bit. So now what we have done is कि हमारे जो पहले abstract एक specification थी that we have a set of free resources. Now we are saying that set, the set will be implemented as an array of bits. So हमारे पास bits हैं, जितने हमारे पास resources हैं उतनी हमारे पास bits हैं, and it will be on and off, and on and off will mean probably कि ये element is present or this resource has been allocated or is this resource free. So what we have done is we have given a concrete implementation specification कि हमने set को कैसे implement करना है, and that is based upon our programming language जिसमें हम इसको implement कर रहे हैं. So the point really is that these refinement steps will take us towards implementation, but at the same time we have to make sure that these refinement steps, they are consistent. So let us go back and look at the mathematical formulations of consistency and refinement and see what operations are permissible and what needs to be done so that we have a consistent model of refinements. To derive a formal definition of refinement and hence a set of useful proof rules, we have to consider the semantics of the operations. An operation may be seen as a relation between states. One state is related to another if the system could start in the first and end up in the second. Our definition of refinement for data types will depend upon a similar definition of refinement for relations. So very briefly, although we have seen this thing before and we have discussed it, but once again, very briefly, a function is a relation from one state to the other. So it takes you from one position to the other, one state to the other. That is what a function is. So it is a map of the state spaces. And this is what we are going to use in our formulations. We have total relations. Refinement of total relations is easily defined. We say if R and S are total relations, then R is a refinement of S is equivalent to S is a subset of R. That is, wherever R relates the same element X to two different distinct elements Y1 and Y2, S may omit either X mapped onto Y1 or X mapped onto Y2. Total relation क्या चीज है? Total relation, we say all elements here, they are mapped onto the elements range and domain. All the elements are totally related. It is possible that one element in the domain is related with two elements on the range, but there is no element on the range which is left alone. There is no element on the domain which is left alone. So this is a total relation. Example of a total relation is, let's say we have a set 1, 2, and 3, and on this set we define this relation less than or equal to. So we have the domain 1 to 3 and we have the range 1 to 3. 1 is less than equal to 1, 1 is less than equal to 2, 1 is less than equal to 3. So 1 is mapped onto all three of them. Now we have 2 which is less than equal to 2 and also less than equal to 3. We have 3 which is less than equal to 3 only. But everything here is mapped onto some element there, and no element on the range is left. So this is a total relation. This is not one-to-one, because in few cases, in the case of 1 and 2, 1 was mapped onto 1, 2, and 3, and 2 was mapped onto 1 and 2. 2 was mapped onto 2 and 3, not 1 and 2, sorry. More than 1. Now this is a total relation. If I had less, for example, the operation less, just less than. So I have this set 1, 2, and 3, and I say, okay, 1 is less than 2, 1 is less than 3, 2 is less than 3, but 3 here is not mapped onto any element on the right hand side. And 1 in the domain, in the range, is not mapped out from any element from the domain. So in that particular case, less than is not a total relation. However, equal is a total relation. 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. But when you look at this equal, this is a refinement of less than equal. There was non-determinism. जब मैं 1 पे था, where should I map it to? Should I go to 1? Should I go to 2? Should I go to 3? There was this non-determinism. So when I say this map is a function which takes me from domain to my range, so my input is 1, I apply this function, where do I go? Do I go to 1? Do I go to 2? Do I go to 3? What do I get? There is non-determinism. I can get any one of these and I'll be okay. Similarly for 2, what are the choices? 2 and 3. Once again, there is a choice. For 3, there is no choice. I refine it. I say my relation is equal to. When I say equal to, now 1 goes to 1, 2 goes to 2, 3 goes to 3. So when I apply this function on 1, I get answer 1. Now this 1 is a legitimate answer in my original specification. If I was getting 1, I would be okay, because I could get 1, 2, or 3. All 3 are legal right answer, legally right answers. So इनमें से कोई भी जवाब मुझे मिल जाएगा वो ठीक है. तो मैंने इसको रिफाइन करके मैंने इसमें नॉन डिटर्मिनिज्म निकाल दिया. I have one-to-one relationship now, and it is not violating my original requirement because it is giving me an answer which was part of the original requirement. So I say S is a refinement of R if R is a subset of S. Okay, so ये जहां पर जरा नोटेशन में जरा थोड़ा सा फर्क है, इसको जरा देखिएगा, जरा बाज़ का कंफ्यूज हो जाते हैं बिकॉज यू नो सुपरसेट और सबसेट का कॉन्सेप्ट जो है ये रिफाइनमेंट में उल्टा हो जाता है. जो सुपरसेट है उसकी रिफाइनमेंट यहां पर हो रही है, वो दूसरी साइड पे यहां पर लेफ्ट हैंड साइड पे आएगा, और इस केस में सुपरसेट आपके राइट हैंड साइड पे जाता है जब आप सेट की नोटेशन के उसमें लिखते हैं, जो सुपर सबसेट की फॉर्म में आप उसको लिखते हैं. सो व्हेन वी हैव अ टोटल रिलेशन, the answer is a straightforward answer. The problem is when we do not have a total relation. What happens in that particular case? Let us go back. To define refinement for partial relations, we consider their totalized forms. Before I go into the mathematical formulation of this, let me explain a little bit. We had this previous example, in which we had this problem of resource allocation. We said, we have this operation allocate, which would take one resource from the free set and allocate, and we specified which particular resource in the subsequent refinement, and then we specified how to represent that set, and so on and so forth. But there was this element of incompleteness. It was partial. And that was, I have this method allocate, this operation allocate, but I do not have anything in my free set. So I say allocate, and there is nothing in the free set. What will happen? So what I need to do is, I cannot work with partial sets. I have to define a total set, and this total set, by making it complete, I will be specifying the error condition. अच्छा, यहाँ पर I will take you back to our algebraic specifications. In algebraic specification, in many cases there, we added this special element undef to many of the types. We said undef is going to be one of the elements which belong to this type. And undef, we will, when we have an error condition or something like that, we will indicate that error condition by assigning this value undef to our output. We'll show undef there. ये undef क्या चीज थी? ये undef was an attempt to complete our set so that we can specify the error condition. मैं कोई भी सेट लूं, I have a set of, let's say, natural numbers. There is nothing undefined there. Now, I want, for example, some operation that is supposed to return a natural number. So how do I indicate an error value? What I return back is a natural number. So I need to have a special value dedicated to signify my error condition. That was what I was trying to do there, that is making it total, making it complete. The same concept, maybe a different formulation here, we will be applying. In this particular case, what happens is, we have to specify the error condition. For example, if our set was less than, so we have this, our operation was less than, and our set was 1, 2, 3. So I don't have anything less than 3 there, because that is what my complete set is. And if I try to apply this function that gives me this less than, I have nothing in the range. So what do I do? Similarly, जब मैंने resource allocation की बात की थी, when I have nothing in my free set, there is no available resource, and I send this message, give me a resource, allocate a resource, what do I do? So I have to somehow indicate that there is some error, and what I do is I complete it with this concept of totalization. So I will very briefly talk about totalization. We will continue this discussion in the next lecture. I don't have time to go into the details there, but now I will very briefly show what totalization means. What we say is, to define refinement for partial relations, we consider their totalized forms, and we say this row dot is equal to row union x colon x, and then this is this inverted T, which is a special symbol. I will be talking about that. Semicolon y colon y inverted T, where such that x is not a member of the domain of row for this operation from x to y. So what we are saying here is, our original method or function was row, the relation was row, so we complete it, and the complete totalization is applied, and what we get back is a row dot, which is the union of row and this new set of elements added to the sets of x and y, and this new x and y's, they are defined as, where x inverted T is equal to x union inverted T, and y inverted T is equal to y union inverted T. That is, we are augmenting the source and destination with a distinguished element inverted T, denoting undefinedness. Okay, so what I'm saying here is, I will elaborate this concept in the next lecture in more detail. But what we have said here is that we had the original domain and range. X was the domain and y was the range, and we had taken elements from x to y. So that was our mapping, that was our relation from x to y. In order to have a totalization of the relation, this relation was not total, and hence that means there were certain elements here which were not mapped onto any element on the range. So I would not get an answer. So what do? I augment both these sets with a special element that is inverted T, and then I define a new relation, and this relation is written as the old relation, and we have a dot on top of that. That is the new relation. And this new relation, what is this new relation and how is that defined? I will talk about that in next lecture. But we define this relation by augmenting the range and the domain with this inverted T, and this basically denotes a special symbol. This special symbol means that we have a case where things are not properly defined. There is a partial definition here. So, like I said, I will elaborate this concept in more detail. This is a very important and fundamental concept in our refinements and making things total from partial in the next lecture, inshallah. Till that time, आप मुझे इजाज़त दीजिए. खुदा हाफिज़ और अस्सलाम वालेकुम.